So, welcome to ESS 21 Lecture 2. I think this quarter is going to go so fast. And today we're going to be moving away from that boring introductory stuff. And instead we're really going to start looking at the tools that we use to look at the Earth system. And that's pretty important because every subject has their own little sort of terminology or vocabulary. And so I don't completely lose everyone. I think it's important that we just go over some of those terms at the very beginning. And I'm afraid you're going to have to think today. I'm going to make you think. It's good for you after all. It's what you're paying for. And we're going to look at some of the data actually that's coming off Greenland. So although we're going to be introducing a lot of terminology, which can be a bit dull, we're going to be directly applying that and using examples from the Earth system related to the cryosphere. So first of all, I just wanted to say thank you very much for everyone who sent me your introductions. I really enjoyed reading them, and I think I have a better sense of everyone in the class now. So thank you for that. I had a couple of quick questions or things that were brought up in those introductions. First of all, I think because everyone was so excited by the video on Monday that I think they may have missed that there is reading for this week. They're really just introductory chapters of that UN Global Outlook for Ice and Snow report, which you can download from the class website if you remember. And it really just introduces the idea of the cryosphere and why we care about it. So please do have a look over that by next week. And then there was something else I was going to say. Oh yes, which is that hopefully you already know that this class does count for various GE categories. But I'm afraid the bad news is that you can only count 2 of those categories. So even though it fulfills 2, 5A and 8, you can't collect all 3 at once. I'm afraid you can only have 2 and 5A or 2 and 8. So I just wanted to clear that up so that no one was confused. So let's have a look, and today, by the end, we're going to introduce the idea of the snowball Earth hypothesis, and that's what my image on the front is today. This idea that at certain points in the past, this is probably what Earth looked like. We were nearly covered by ice and snow, and so we're going to look at some of the situations or some of the conditions that allowed that to happen, as well as how we then rescued ourselves from being a frozen ball of ice forever. So these are the learning outcomes for today. So by the end of this lecture, you guys are going to be able to do a lot. You're going to be able to identify and understand the implications of open and closed systems. We're going to be able to identify reservoirs, sources, and sinks of a system and make simple calculations of what we call residence times. And also we're going to be able to look at feedback loops and say whether they're positive or negative. And the key thing about these, which is confusing at first, is that positive feedbacks aren't necessarily things that are good. Usually if you get positive feedback on something, it means that you've done a good job. Positive feedback in the ESS, or Earth System Science terminology, means something a little bit different. So we'll stress that as we get there. So this is what I showed you on Monday. And you all very sort of carefully got your pen and paper out and noted it down. But what you should have said to me is, one Earth is a reservoir, one Earth is a system, because those have quite specific definitions. And so definitely we said that we split up the big sort of major Earth system into these 4 different component parts, but we didn't really define those words, those sort of reservoirs and systems. So we're going to start by looking at systems. And you can see that on my diagram here, I have 3 types. I have an isolated system. And an isolated system doesn't exchange anything with the surrounding environment. It doesn't exchange energy, and it doesn't exchange matter. And in reality, doesn't exist. Okay? So the nice thing is that we're dealing with the real world here rather than the theoretical world. And in the real world, that just doesn't exist. There's always exchange of energy between things, even with your thermos flask, whatever else, keeping your tea hot or your coffee cold or however else you have it. There's still small amounts of energy being transferred there, and so it's still not an isolated system. So you have a 50-50 chance always of getting it right when I ask you whether it's an open or closed system. And so let's look at those other 2 more carefully. So when we say what a system is, we're really arbitrarily defining a boundary. So this room could be a system, and the boundaries could be the walls and the doors. Or UCI could be a system, or the US could be a system, or the lake or the pond or something could be a system. We're just sort of defining where those boundaries are. We're isolating it from everything else. And so closed or open systems, really, whether they're closed or open, it depends on whether they transfer matter. Because both of these will transfer energy. It's really very, very difficult, if not impossible, to stop the transfer of energy. But open systems will exchange matter across those boundaries. So for example, if people are coming in late, we're going to be an open system because things are moving through the boundaries as well as air, hopefully, and everything else. So this classroom would be an open system. We're exchanging matter across those boundaries, as we just saw. But with our closed system here, shown in the middle diagram, in this example, it's sort of sealed shut. It's airtight. So even though we can get energy coming in from the sun and warming it up, we're not actually exchanging any sort of elements or atoms or anything else like that across that boundary. Does that make sense? Hopefully? Good. So, prove to me it makes sense by thinking about it for a second. Is the Earth an open or a closed system? And I've also given you a couple of other options. Is it a mostly open system or is it mostly a closed system? So tell me what you think the Earth is. You can consult your neighbour as well if you want and persuade them of your answer. And there's a couple of seats open near at the front if you guys want to come down. So I'll give you until a minute to decide. So any last answers have to be in by a minute. So let's take a look at the results and we'll see whether we've reached a consensus as a class. That's a definite no then. Okay. So let's think again about our definition. So, remember a closed system is more or less like that sealed beaker. It can exchange energy, energy can come in and it can warm it up and it can leave that system, but no matter is being exchanged. Our open system is one where we're both exchanging matter and energy across those boundaries. What is the thing on this image surrounding Earth? What's it called? Space. What is the thing about space that means that we call it space? What's in space? Yeah, well, everything and nothing, right? But in general, it's a vacuum, right? There's not a lot up there. So think again about, are we exchanging energy? Are we getting energy from anywhere? Are we losing energy from the Earth? And also think about matter. Are we gaining anything, like atoms and elements and things? Are we gaining anything from space? Are we losing anything to space? Okay, so I'll ask the question again. Think about it again. Consult your neighbour. Consult the people behind you. See if you get a different result this time around. Okay, just a few more seconds for the last few votes. Right, we'll take a look and see what our answer is this time around. So we've shifted a bit. We've shifted to D, and I'm glad about that because it would be the right answer. Okay, so it is mostly closed. So where is our energy coming from that fuels us, the biosphere, the climate? The sun, absolutely. So we have energy arriving to Earth from the sun, and we also radiate energy out to space. Okay? What about matter, though? Are we losing any matter from the Earth? What was that? Astronauts. Well, hopefully we don't lose too many. Hopefully they come back again. But yes, you're absolutely right that we've put up a lot of satellites at least. So we are losing. But compared to, say, the mass of the Earth, our little satellite that we've put up is really not very significant, is it? We're actually losing a couple of other things to space. Does anyone know what we might be losing? Helium, absolutely, your lovely helium balloons. Unfortunately, whenever we get helium, helium is actually mined. Did you know that? It's weird, right? We don't extract it from the atmosphere, we actually mine it from underground. And so there's only a finite amount of it, because as we release it from our helium balloons, it goes into the atmosphere, and it's light enough that it actually then can escape Earth's gravity and head out to space. And it's exactly the same with hydrogen. So remember, hydrogen and helium are our lightest elements, and so we lose both of those gases out to space. What about what's coming in? Asteroids, absolutely. Last year we had a very good example. Or was it? Yes, it was last year now. That asteroid, or the meteor that came down over Russia. In reality, we're getting hit by sort of thousands, hundreds of thousands, millions of little tiny pieces of dust each day, and they're incrementally adding to the Earth. But again, compared to that enormous sort of thousands of kilometer thick sphere of rock, then we're not really adding very much. So you're absolutely right that we're a mostly closed system, okay? So energy can enter and leave the system, but the vast majority of the matter doesn't enter or leave. So here's what happens to our energy. We get energy from the sun. We're sort of intercepting that energy as it spreads out in all directions. Some of that just gets reflected straight back to space, but some of it gets absorbed by the Earth, and that gives us a temperature. And anything with a temperature radiates energy. And so we're also radiating energy out. So we're definitely exchanging energy. And you're right that coming in we have comets and meteorites. And today that's not very much, but actually in the past that was much more important. For the early Earth, it was basically how the Earth formed by all of these collisions. And out we're losing our satellites, but also hydrogen and helium are drifting away. But it's mostly a closed system. And there are some implications for that. And they're ones that I think are pretty familiar to anyone that's sort of living in the modern world now. And that is that our resources are finite. If we use all of the aluminium or aluminum or whatever you want to call it on Earth, then we're going to have to go somewhere else to get it. We can't sort of magically create it. And that's why people are talking about asteroid mining and crazy ideas like that, to go and get some of these metals that are so valuable to us today, but which are finite. There's only so many of them on Earth. We also can't throw things away. There is no a way to throw things to, short of blasting things out to space. And so things like when we throw out our garbage, we think of it as just going away. In reality, for anyone that's ever lived near them, you know that we have these massive landfill sites, and we have problems with disposing of more hazardous things like nuclear waste. And the other thing is that changes in one part of the system will therefore affect everything else. So for example, if we're melting ice right now, that melting ice just doesn't disappear off magically somewhere else. It goes somewhere, and where it's going right now is into the oceans, and therefore we see sea level rise. And so that's what we say when everything's interconnected, because we are a closed system. It's not going anywhere else. Everything sort of stays on Earth and just moves around between those different places. Okay, so if we want to study the Earth, which is a really complicated system, there are a few things that we can do that will help us out. And the first thing that we can do is identify the components of the system that we're interested in. And that can be pretty simple if we're just looking at a lake or something like that. Or it can be much more complicated, say if we're trying to study the climate system with a lot of interacting parts. The second thing is we can look at something we call the residence time. And the residence time is just a measure of how long my little atom or molecule of whatever I'm interested in will stay in that particular place, will stay in the ocean, or will stay in the atmosphere before being moved elsewhere. And then the third one, and one that's really important for the cryosphere in particular, when it sort of is part of the climate system, is feedback loops. And feedback loops are basically interactions between elements that either amplify a change or can stabilize that change. And we'll have a look at a couple of examples. I think it's difficult to imagine it right now, so we'll come back to that at the end of today. And so we can do it manually for simple systems, but for really complicated systems, the maths gets too crazy way too early. And so that's why things like computer models are so helpful for understanding the Earth, and why we've made such great strides, really, in recent decades in understanding how the Earth system functions. So a few definitions for you. So when I talk about a reservoir, I mean the amount of material that I'm interested in a given form. So my example here is my lovely bathtub. And in this case, the reservoir would be the water in the bathtub. That's what I'm interested in. That's my reservoir. Okay? And then we have fluxes. And fluxes are that material being added to that reservoir and material leaving that reservoir. And in particular, our flux, which adds material, is called a source, unsurprisingly, hopefully, to most people. So a source of water to my reservoir might be from the taps. Okay? In terms of being removed from that reservoir, it's called a sink. And it just happens to be that it's sort of bathtub related, but you can have a sink from the atmosphere or something for carbon. And in this case, that sink would be water flowing out of the bathtub through the plug. Okay? And so if I say that my bathtub is in steady state, then I'm saying that there's no net change in the amount of material. And if I've got the plug in and I've switched off the taps and it's not changing, that's fine. There's nothing coming in, nothing going out. It's at steady state. But you could also look at it as if I've got the taps turned on full and the same amount is draining out at the bottom, the level of the bathtub isn't really going to change, right? The level of water in there is also going to be constant. And that's what we call steady state, when the size of the reservoir doesn't change. And it's usually because we've got the same amount coming in as we have leaving. But if we think about this for a second, if I have my taps on full and water's draining out of the bottom of the bathtub, even if the level of the water is staying the same, I'm not going to have exactly the same atoms of water in that bathtub the whole time, right? They're going to be changing over. And that's where the residence time comes in. That's what that sort of tells me, say, when my water molecule gets added to that reservoir, say from the taps, how long on average it tends to hang around in that reservoir before it will leave. So that's my residence time. And it's also, if you think about it another way, it's also that sort of time that it would take to either fill or empty that reservoir. And so there's a very simple equation, and there's only one thing that happens that causes people to get this wrong. And that's the big OR in the center of that equation. Circle it in your notes, make a big sort of note about this, because when we do these calculations, we say that the residence time is equal to the amount in my reservoir, but I'm going to divide it by the total sources, so the total amount coming in, or the total amount leaving. Okay? So make sure that you only use one or the other. And in the examples I give you, they're never going to be different. Okay? And so always make sure that you just use one or the other there. Right. So bathtubs are all very well for explaining the concept, but they're pretty boring things. We're not going to learn a lot by studying a bathtub. Instead, let's look at something a lot more interesting, and particularly related to the cryosphere class, and that is the Greenland ice sheet. So hopefully everyone knows roughly where Greenland is. It's sort of between North America and Europe, near the Atlantic Ocean. And the figure here shows that we have this sort of big, sort of 3-kilometer thick ice sheet sat over much of Greenland, apart from maybe the very edges. And it has been changing, and that's perhaps not surprising. It might change gradually through time, but more recently it's been changing much more dramatically than that. And this sort of the colors here, the blue represents a decrease in the height of that ice sheet, basically a melting of that ice sheet. The red is sort of representing an addition of snow or ice to that ice sheet. And you can see that around the edges we've been losing a lot. We've been losing maybe 60 centimeters per year, which is sort of that much per year, which is quite a lot of ice for a very large area. Okay, so let's look at this more carefully. So if we're going to study the Greenland ice sheet in those ways that we just talked about, then the first thing we have to do is identify the components of the system. So for the Greenland ice sheet, what is going to be my reservoir? The ice sheet, yes, absolutely. We're not doing anything too complicated here. So yeah, absolutely. My reservoir is going to be my ice sheet. There we go. There's my ice sheet. The ice sheet on Greenland is very roughly about 3 million gigatons, and a gigaton is a billion tons. So it's 3 million billion tons. It's a lot of ice. Okay, it's a lot of weight on Greenland. But all of our units are going to be in gigatons, so we just need to look at the 3 million right now. So now let's think about my fluxes. How are we going to add ice to Greenland? Yeah, absolutely. Everyone sounds so uncertain because it's so obvious. It is obvious. It can snow on Greenland, and over time that snow will be compacted and turned into ice. So yeah, our fluxes to Greenland are the snow, and that's our source to Greenland. What about our sink from Greenland? Yeah, melting, absolutely. So a certain amount of that ice is melting, and that would be our sink, okay? So our snowfall is our source, and that's about 150 gigatons per year. And our melting is our sink from the ice sheet, and that's also, in my example here at least, about 150 gigatons per year. Okay? So my first IQ question of the day, second, is this system in steady state? And what does that mean about the overall mass of the ice sheet? So my example here, think about whether it's in steady state, and what does that mean about the mass of the ice sheet? Okay, a few more seconds for the last few votes. Great, I think that's everyone, so let's take a look. Overwhelmingly A, and that's great because that is the correct answer. Okay, so it is in steady state in my example because our addition each year of snowfall is 150 gigatons per year, but we're also losing 150 gigatons per year. So our inputs equal our outputs, and so we're at steady state. The overall mass of the ice isn't changing. Okay, so hopefully that makes sense. So that's our first part, and really it's as simple as that. The second part is determining the residence time. So you know what's coming. I'm going to get you to do some maths. So if our residence time equals the total amount in the ice sheet divided by the total sources or sinks, now you have to think a bit. What is going to be the residence time of a little molecule of H2O in that ice sheet? So do some cancelling. See if you can do it in your head. So I'll give you until a minute. Do some speed math. Great. So let's take a look and see how good everyone is today, with or without their calculators. Ooh, best yet. Good, and it's even the right answer, which helps. Well done. So yes, and it really is as simple as that. So don't get caught out. Really what we're just doing there is we're saying that the amount in my reservoir is my 3 million, and then the total sources or sinks, remember, is either that 150 coming in or the 150 going out, and that leaves us with 20,000 years. And that's a pretty long time, which isn't really surprising because it's such a huge, huge ice sheet, and we're only adding and taking away a tiny amount each time. So it should be pretty unsurprising that, therefore, that little molecule of H2O spends a very long time sat in that ice sheet before it melts away. Okay, so that's all very well in my perfect world, but the Greenland ice sheet is changing. And in particular, I wanted to show you a very quick video showing you exactly how we work that out, because obviously it's very difficult to measure something that is 3 million gigatons. So this is something that Sasha also uses in her research. So you can also ask her about this as well.
So much ice that if it all melted, it would raise sea level around the world by a whopping 23 feet. Okay, so it's not all melting, but scientists say a warming climate is rapidly turning a lot of that ice to water. But exactly how do we know? Thanks to a pair of 1,000-pound satellites with a rather dainty name.
We picked the name Grace as gravity recovery and climate experiment.
Byron Tapley is the proud father of these twin satellites that launched in 2002 and to measure changes in gravity. Separated by roughly 135 miles, the distance between the two GRACE satellites grows and shrinks depending on the pull of gravity. The stronger the tug, the heavier the mass below them, the greater the distance between the satellites. And by passing over the same area roughly once a month, this dynamic duo can track extraordinarily small changes in mass.
You can see not only the annual change, but you can see the actual decadal-type variation.
GRACE is particularly amazing when it comes to measuring changes in water, like the reduction in groundwater in California's drought-stricken Central Valley. GRACE can also see that Greenland is melting at a rapid rate. In 2007 alone, Greenland lost 217 billion tons of ice. That's like San Francisco Bay draining every 10 days for an entire year. That's a lot of ice melt, and it's contributing to a steady rise in sea level around the world. I'm Dr. Heidi Cohen of Climate Central with the GRACE satellites. And that's how we know.
Okay, so that's sort of some of how we do it. We have learned so much by using satellites to study the cryosphere, and in particular, that's the only way we're going to really be able to study something as huge as Greenland, and also we use the same thing for Antarctica. And I think that's pretty amazing that we can use these little satellites that use changes in the amount of gravity that they feel due to that extra loss of mass from Greenland. That mass then gets distributed into the world's oceans. It can actually sense the slight decrease in gravity because of that loss. So that's really cool, and ask Sasha about that as well, but she uses that to study groundwater in the Central Valley. And so if we take that data, this is produced by one of the researchers actually in our department. By processing all of that lovely data, we get a graph that looks a bit like this. And it looks a little complicated at first, but it's not. So here is 2002 at one end, and here is 2010 at the other. And that black line basically shows you whenever it's going up, okay, so gigatons on the y-axis here, whenever it's going up, we've got addition of ice to Greenland. And so what season do you think that probably represents? Winter, absolutely. What about when we see a decrease, that will represent the melting, so that will be summer, obviously. And so you can see what's been happening over those years when we've actually got real data to look at. And I want you to spend a bit of time thinking about this more carefully. And so in groups of 2 or 3, and the TAs will get up and wander around as well and help you out with this, I want you to look at roughly how much snowfall there is each year in terms of how much mass is added to the ice sheet. Is there a trend in the amount of snowfall that's happening? How much melting is there each year? How much mass is lost each summer? And is there a trend in that as well? And so what has been happening to the volume of the ice sheet? And then use those numbers to work out, if we're losing that sort of net amount each year, how long will it take us to melt away the whole of the Greenland ice sheet? And then for the last bit, if you're all done with that nice and fast, then think about some of the assumptions that you made. Think about how accurate your estimate might be, what else might come into play, okay? So spend 2 or 3 minutes doing that, or probably more like 5 or 6 minutes doing that, and I'll wander around as well and answer any questions. Okay, so how are people doing with this? So someone asked me a very good question at the front, was sort of, what does 0 represent? 0 sort of represents like an arbitrary, we just said, well, that's, in that year we'll say that there's 0, and then anything above that. It's just easier than plotting 3 billion gigatons plus and minus sort of something, okay? So 0 is somewhat arbitrary. The key thing that anything goes up is we're adding, anything that goes down on that graph is we're taking away. So roughly how much snowfall in gigatons do we get each year? Yeah?
Roughly 200.
Yeah, roughly 200 or so. And did you see any trend necessarily over that 7 or 8 years?
Yeah, we gain about 200 and then lose about 400.
Yeah, absolutely. So we seem to be gaining about 200 and losing more like 400, which obviously isn't steady state, and it's not good news for Greenland. Did anyone notice anything about how much melting we're seeing in each successive year? Yeah, absolutely. That rate of melting, the amount of melting that we see each year, seems to be accelerating. And so that's why we have this sort of curved line Because if the amount that we were adding and losing was the same each year, it would just be a straight line, and we could just project that straight line down. But what's really worrying us right now is that we seem to be seeing not necessarily any more snow, but a lot more melt each year. And so what we're seeing is that the overall mass of the ice sheet is accelerating its loss. It's losing more and more each year, and so that's a concern. So did anyone manage to do the calculation to work out how long it will take to melt the ice sheet? Someone yell some numbers at me. So someone says 30,000. What was yours? 10,000, 15,000. So it might depend a lot on what value you take, okay? But in general, it's usually at least 10,000 years or so. And remember, this ties back to what I was talking about on Monday when I was saying that snow is really sensitive to changes in temperature because it's really thin. But even if our temperature rises by a lot, it takes a while to melt a piece of ice as big as Greenland, even if we're taking off more and more each year. And that's why when people tell you that sort of Greenland is going to melt by 2100 and we're going to have 6 meters rise of sea level, we're definitely worried about how much it might melt and how quickly it will melt. But we're not going to lose the whole of the Greenland ice sheet that fast. It's just really not sort of possible with the physics that we think is going on. Okay. And so the last question, how realistic is your estimate? And what are we assuming when we make that estimate?
That it'll continue to increase 200 and decrease 400 every summer.
Absolutely. We're assuming a constant rate of loss. And actually what we said is that it looks like it's accelerating. And why might it be accelerating? Why might it accelerate in the future?
Climate change.
Climate change, yeah, absolutely. It's getting hotter each year. That's a concern. And so the concern is that if we keep increasing temperature, we are going to keep increasing the rate of that loss. And so what you're estimating there is potentially a sort of a minimum number. In reality, it might get a little bit faster than that. And the other thing is things like, if you want to go somewhere cold, do you remember we said we would go up in altitude? If we're melting away the ice sheet, it's getting lower and lower and lower. And so it will get warmer and warmer and warmer as it gets lower. And so that also might accelerate the ice melting, okay? We haven't necessarily talked about snowfall amount, but that's much more difficult to actually get an estimate of. So this is the sort of thing that I like to do, is actually show you some real data and allow you to look at it and think about what that really means for us. And I think that's sort of something that's nice and easy to do. So that ended in 2010. So shall we have a look at what it is today? Are our trends continuing? Yes, absolutely. So we stopped our graph in 2010 or so, and so we have another extra sort of 3 years. 2013 was a much better year. We didn't lose as much in melt, but you can see that 2012 in particular was a really spectacular year in terms of ice loss from Greenland. And if any of you watch the news, you might have read that for the first time that we have observed, at least with our instrumental records, the whole of Greenland melted. Even right up at sort of 3 kilometers height where they drill the ice cores, they'd never seen it, but the whole ice sheet was above zero and started melting in the summer of 2012. And it was a really very unusual event. And the question is that going to remain a really unusual event, or will it become slightly more frequent in the future? So there's some really interesting stuff about Greenland online if you would like to know more. Okay. Does anyone have questions about that? No? Yeah.
What was the formula to figure out D?
The formula. So I quite like using what I call intrinsic math. So math that you sort of know how to do, but you don't know how to do it. And so really the idea is that the formula, if you like, was if you work out how much loss was happening each year. So you basically take how much loss minus how much snow was added. And that sort of gives you the net loss each year. And then you just divide that 3 million gigatons by that net loss, and that gives you a time frame. Okay, great. Anything else? Okay, in that case, let's move on to feedback loops, because feedback loops are something that we're going to come back to again and again. You're going to get so sick and tired of seeing feedback loops by the end of this class. So, do you remember I said at the very beginning that we use funny terminology, and we don't do it deliberately to confuse you, but unfortunately that's what happens. So this is when an output of the system affects the input, and so it gets all very circular, but it is really important for the climate system. And we have two types of feedbacks. They can be positive and negative. And remember, that isn't anything to do with our desired outcome on climate. A positive feedback is not something that is good for climate. A positive feedback is what actually is an amplifying feedback. So an amplifying feedback is something that might take an increase in temperature, and because of how the Earth system functions, there might be a sort of a loop that leads to a further increase. A negative feedback is a stabilizing feedback. And in this case, maybe we take on an increase in temperature, and our little feedback loop of various components of the system lead to a resulting decrease in temperature. It's stabilizing us. And so in general, for climate, we really quite like the negative stabilizing feedback loops. It stops things getting out of control. So let's take a look at a couple of examples. So my first example is a negative or a stabilizing feedback loop, and it's one of the simplest ones I could find for the climate system. And we use a specific sort of notation for this. So if an increase leads to an increase, we call that a little positive coupling, and we draw a normal looking arrow to represent that. If in fact an increase leads to a decrease, or a decrease leads to an increase, so a reverse change in what's happening, then we actually draw an arrow with a little circle at the end, and that's our negative coupling between two boxes. So first of all, let's take a change that we know is happening today, an increase in the amount of CO2 in our atmosphere. If we increase the amount of CO2 in our atmosphere, what do you think happens to plants? Do you think they find it easier to grow or more difficult to grow? Easier, yeah. Why do you think they might find it easier to grow? Yeah, absolutely. The photosynthesis process, they take in that CO2, they combine it with water to make sugars. And so if we increase the amount of CO2 in the atmosphere, it's easier for them to take it in. So if we're increasing CO2, what will happen to the amount of plant growth right now? Yeah, it increases. So am I going to use a nice normal arrow or an arrow with a circle at the end to represent that? A normal arrow. You've got this. Okay. So we have a nice normal arrow linking those two boxes. But if we're growing a lot more plants and they're taking in a lot more CO2, what is going to happen to the CO2 concentration of our atmosphere? It's going to decrease again, absolutely, because we're taking that CO2 out and we're putting it into plants. Okay? So in this case, an increase is leading to a decrease, so what arrow will we use to go back the other way? Yeah, an arrow with a circle on the end. Have I lost you? Do you want me to go through that one more time? Yep, okay. So let's go back to the beginning. We have these two boxes, and what we want to do is look at whether a change in one will cause any change in the other, and whether that will feed back in any way. And in this case, it does. So we're seeing an increase in CO2 in the atmosphere. As that happens, plants are more easily able to take in that CO2, and so they grow better. It's what we call plant or CO2 fertilization, and it is happening today, we think. And so if we're increasing the amount of CO2, we increase the amount of plant growth. And so what we do is we draw a nice normal looking arrow to represent that, because in this case an increase is leading to an increase. Okay? But if we're going to increase the number or the amount of plant growth that's happening on Earth, then that extra plant growth is going to take in that CO2, and so in turn it's going to start lowering the amount of CO2 that's actually left behind in our atmosphere. And so in this case, an increase of plant growth is leading to a decrease in the amount of CO2 in our atmosphere. An increase leading to a decrease is what we call a negative coupling, and to represent that, we draw a little arrow with a circle. Okay? So that's what that represents. And so overall, if we look at where we started, we increased the amount of CO2 in our atmosphere. As we followed that loop around, that entire loop led to a decrease in the CO2. So in this case, our loop starts with an increase and it ends with a decrease. And in that case, it's a negative or a stabilizing feedback loop. It's trying to oppose any change. And that's why it's a good thing. It sort of helps us out in some way. And so that's why we like these. So let's look at a positive feedback loop now. Let's look at this one. So this is one that's particularly relevant to the cryosphere. And so in this example, I have a completely dark Earth, my black Earth, and then I have an Earth that's half white on the top and half black at the bottom. And you can imagine that with the incoming sunlight in the same in both cases, this one will absorb a lot more of that incoming energy. That sort of black surface, if any of you have ever been to the Phoenix Grill and they have those black tables outside, you know that if you put your hand on them accidentally in the summer, then you burn yourself as it gets so hot. And so that dark surface absorbs all of that incoming energy. In contrast, when we have all of that nice white surface on there, it reflects back a lot of that incoming radiation. And so that Earth absorbs less of that incoming heat, and so it's slightly cooler. Does that make sense? Yeah. So I have a challenge for you. Okay, so let's sort of see whether we can draw that feedback out. So I'm going to give you a couple of minutes again. And so now I want you to think about what would happen if you increase the temperature of the planet. Okay? If you increase the temperature of the planet, what will that do to the amount of ice? What will that do to the amount of sunlight reflected from the Earth? And what will that therefore do to Earth's temperature? And again, yeah.
Do you want me to answer it?
Oh, I'm going to give you a couple of minutes and then you can give me your answer. But again, the TAs will wander around and give you a hand with this if you would like. Okay, so a couple of minutes because we are running out of time. So what do you guys think? So if I increase the temperature of my planet, what am I going to do to the amount of ice?
Decrease.
Decrease. So what sort of arrow am I going to draw there? Circle, absolutely. And as I decrease the amount of ice, how much am I going to be reflecting back to space?
Not as much.
Not as much. So in this case, a decrease is leading to a decrease. It's an arrow. And then what happens if I'm decreasing the amount of sunlight reflected? It's going to increase, right? Yeah, absolutely. You guys got this. Great. Okay, well, I'm afraid that we're running out of time, so I'm going to have to move on. But hopefully you've had a chance to think about this. So if I increase the temperature of my planet, what do I do to the amount of ice? I decrease. So what sort of arrow am I going to draw? The circle at the end. If I'm decreasing the amount of ice, how much sunlight am I going to reflect? Less. So what sort of arrow am I going to draw? So I've decreased the amount of ice, and that leads to a decrease in the amount of sunlight reflected. So it's a normal arrow. If I'm decreasing the amount of sunlight reflected, what do I do to the temperature of my planet? Increase it. So what type of arrow is that? Circle. And you can do the reverse. You can say if I decrease the temperature of my planet, I increase the amount of ice, which increases the amount of sunlight reflected, which decreases the temperature again. And do you remember I mentioned the snowball Earth? This is actually something that happened, this positive feedback loop, this amplification. So we start off with a small decrease in temperature, and as we grow more ice, we decrease temperature even more. And you can see that over time, Earth developed its cover of ice. Okay, so we'll end there for today, and we'll continue on Friday with the planetary energy balance.